Kisa from National Zhongshan University. He will talk about time frequency correlation of repeating phase radio bursts. So let's welcome the speaker.
Okay, thank you for the introduction. So I'm Shotaro Yamasaki from NTHU. And here is the image of the world's largest single-dish telescope called FAST in China. And this study utilized the dataset obtained by this telescope. And this paper is already published in APJ letter this year. And also, I don't have maybe equations, so don't worry. So I like fast radio burst, and I'm studying fast radio burst. And they are the brightest radio flash in the universe. And actually, I show here the signal of the fast radio burst. And you can see at the top, it's a light curve, and it's only lasting for a few milliseconds. It's very short. And you can see in the bottom, it's the frequency versus time, showing this is dynamic spectrum. And the lower frequency actually arrives faster earlier than the higher frequency due to because of the propagation effect. The FRB propagate across the intergalactic space, and so they get some propagation effect. And they are very distant. Redshift could be up to maybe redshift 1, which makes them very bright, up to 10 to the 40 L. And also, most importantly, also some FRB. Usually, FRB is found as a single pulse. However, some sources are known to repeat multiple times from the same direction. So we don't know what's going on regarding the entire population. And origins are largely unknown. However, one possible candidate for fast radio burst generation is magnetar. Magnetar is the special highly magnetized neutron star, and it's the strongest magnetic field in the universe, which can power fast radio burst, but we don't know yet. Then here is the motivation. So as I mentioned, maybe several nearby repeating sources are kind of very extreme in terms of its repetition rate. It produces already 10,000s of bursts from the same source. You can see here, they are all fast radio bursts, different fast radio bursts, but coming from the single source. And this is only a part of it. And now this forms a very rich data set, good time series data set of fast radio bursts. And these data are publicly available. So why don't we use it? This is the motivation. Then the theme of this talk is about time series data set. And fast radio burst, for example, have a lot of parameters. Each burst has, for example, arrival time at the Earth, and also the time duration of the event, typically at millisecond scale. And also frequency, so it's radio pulse, so it has a frequency information around the gigahertz frequency, and also so on, so flux or energy, whatever. And then the most important thing is we have a huge data set, so this is kind of big data, and what kind of parameter we use and what kind of analysis we do. This is very important for data-driven analysis. Then my choice would be something like this, combination of the arrival time of the fast radio burst and also spectral peak frequency. Why? First, spectral peak frequency is defined as the peak of the time-integrated burst spectrum. This is the same as similar to previous figure, dynamic spectrum. This is the light curve, and they show on the horizontal axis, they show the kind of SED of the fast radio burst. So from this plot, the peak frequency is around 1.2 gigahertz. And this quantity is interesting because theory predicts something unique about peak frequency. So fast radio burst has, roughly speaking, two types of emission mechanism, which both involve a neutron star at the center. But in each model, peak frequency is directly related to the local condition and the environmental parameter, such as magnetic field geometry, the height from the neutron star, as well as the also plasma frequency, which means number density of the electron-positron plasma. So the peak frequency has direct emission of the hidden environment of fast radio burst. So this is very interesting to look at. Then the method is also important. I have now thousands of burst information from the same source. And I use only two parameters, arrival time on the x-axis, and the y-axis is the peak frequency. This is a schematic example in the T-mu space. Then, let's consider some correlation. Let's choose random pair on this panel. Then, we can define the time difference between these two bursts. This could be positive. Then I define as positive, and then the peak frequency difference on the vertical direction, this can be either positive or negative. Then, on the right panel, I show delta t, delta nu space, and let's count pair on this panel, and let's make the map of the count on delta t, delta nu space. So basically, I take all possible pair on this panel. Then we do this analysis for first to the observed time series. Then also we compute the expectation from the random expectation. Basically, we consider a randomized data set and we can also count the number. Then the correlation function is defined as the excess of the observed burst pair in each bin compared to the random expectation. So if we have more observed data, we see stronger correlation. So this is the basic idea. This is the only equation, by the way. Then here are the data set. So here I show three very famous fast radio burst sources. It's already localized to the host galaxy, dwarf host galaxy at very nearby universe. And basically these are intensely observed in the early era of fast radio burst field by past. First Arecibo is already gone, but the past has taken over its role. And here are the data set. So basically I use about 4,000 events which have new peak information. Then I make 4 data sets. Then basically the observation of the single reach telescope is only kind of limited amount of time per day. And they continue this monitoring every day. So it spans across many days. So for each day, I need to consider continuous monitoring observation, not to lose correlation. So I can't consider separate day observation. It's too long to keep correlation. So I count the burst pair within each day, and I sum up all of them across different observation group. Then here is the result. Okay, so this is the data set from the first repeating fast radio burst, most famously repeating fast radio burst, called 12-1102A. Then x-axis is the time separation between burst pair. The y-axis is the time difference of the peak frequency between pair. Then, as you can see, so the color shows correlation strength. Guzai means the correlation, and here the kind of light blue color shows no correlation. Guzai is near almost zero. However, if you go to short time separation between burst pair, it has significant correlation. And this trend is already known in the previous paper, so I confirm this trend. Then what's new about this result is the dependence on the peak frequency, correlation dependence on the peak frequency. Actually, there is a non-uniformity along the y-axis. So this looks interesting. And actually, this looks universal across all data sets. So basically, the peak location of the correlation is kind of this part, so lower left part. The negative peak frequency shift has the strong correlation. So let's quantify this correlation. So now I consider only short time scale bins and integrate the data along the t direction. Then I want to see the dependence of the correlation on the frequency. Then this is the result. So magenta color show the data set, or observed data set. And it has a kind of stronger correlation at negative peak frequency shift. Then also teal color data, it is kind of shuffled data set. So by shuffling, we can kill correlation. So as expected, we don't see any dependence on the nu in T kind of bluish color. So actually, we confirm there is a significant difference from random expectation compared. So basically, this kind of clockwise rotation trend is significant. In this case, this is about 5 sigma significance. And this means basically that if first radio burst occur, the second burst always tend to have the kind of smaller peak frequency. So this is kind of statistical implication. Then also I tried this analysis for other sources, and overall we see strong correlation, and it is about 6 sigma. Okay, so let's see the discussion. So here I show this is the one burst, and this is the kind of phenomena known as the sad trombone effect, because in a single pulse, the peak frequency of sub-pulse goes down. So basically, like sad trombone effect. This is famous phenomena. However, we didn't know the origin. This is happening on very short time scale, about 1 millisecond. Then our result actually capture for the first time this phenomena statistically. So you can see the shortest time scale range. We see this phenomena indeed. Then not only we see this phenomena, but also we confirm this phenomena is actually as a part of extended view. So basically, this is continuous trend up to longer time separation. So basically, if you go to shorter time scale, the negative peak frequency shift is more significant. Then finally, this is the kind of interpretation, model-free interpretation. So let's see. First, when FRB happens, main shock happens, that this may change the surrounding environment of the local plasma. By, for example, if the neutron surface have some maybe fracture, then the environment change. And also maybe plasma ejection in the magnetosphere may change the number density of the plasma. So this, if the next event happen, right after this kind of event, we see new peak decrease. However, this only lasts up to some 0.1 second, and this may be controlled by the persistence of the environment, or maybe geometric effect, neutron stars rotating. Then, if the next event occurs after this time scale, because this phenomena, this event doesn't remember previous environment, so that this kind of correlation is lost. So this is a kind of model-free interpretation. And why peak frequency decreases, this may be also another issue we need to discuss. For example, plasma density may decrease and decrease if the new plasma is pushed toward the shock region. So this kind of interpretation is also possible. Okay, so this is a summary. So basically, we use very old method to new phenomena, fast radial burst. And these data sets are all publicly available. And so statistical approach is now very powerful to study unknown phenomena. Thank you so much.
Sure. So very nice. When you integrate over the time,
Yeah.
I saw in a larger delta nu, there's a negative correlation. Is that artifact or is this serious? I'm sorry, when the next one?
Sorry, what is your question?
Next one. Next slide.
Okay.
If you go to large one, the correlation is sort of negative, right?
Yes.
So, is this real meaning, or is this just an artifact of the limited bandwidth?
No, this is. I don't think this is the artifact. This is happening, really happening. Why do you expect this is artifact?
Because your frequency range is limited, so if you go down, then it has to come back somewhere.
Actually, also the frequency range is limited, but the within this frequency range, this is really happening. Mm-hmm. And of course, there might be some observational effect. Telescope has some maybe efficiency across band. So maybe this kind of effect might be tested in the future, but we don't know what kind of effect there is. And at least this kind of effect doesn't matter as long as the shortest time pair is happening at the same frequency range. So basically, if the first burst I think this kind of phenomena is happening uniformly across the observational band. So I don't think this is an artifact. So maybe I can explain
do
later.
you have any physical explanation?
Physical explanation of this? So for example, if neutron star is kind of have a beam and it is rotating like a magnet about 1 second rotation period, then within each beam has some size. So if beam is passing our line of sight, this time scale can be maybe around 0.1 second. If beam is not seeing us, we shouldn't see first, right? So this kind of geometric effect could be maybe one possibility, but we don't know yet. So this is very interesting kind of point, and I need to make theory for this.
Okay, thank you.
Thank you.
So let's thank the speaker again. And now let's thank our speaker in these sections. Okay.